Hello everyone and welcome to lesson 3.1, our introduction to corrosion. If you had a chance to look at part 1, then you would have watched a few instructional videos and had the chance to think through some questions that gave you a basis in chemistry for what we're about to learn here. If you haven't done that, I invite you to do so. It's very helpful. But just to give you a quick recap of what we discovered in that previous section, we talked about atoms and how atoms have different parts of them. There are neutrons and protons and electrons. And when you have two different types of elements or atoms of elements together, they very often, when the circumstances are right, want to share electrons with each other. An electron, when an atom loses an electron, that's called oxidation. But when another atom gains an electron, that's called reduction, because it's reducing the positivity of that force. So electrons are negative, so when you gain an electron, you're reducing the positivity of your atom. We talked about stuff like this, but now the big question is, what does electron transfer have anything to do with corrosion? Because that's really, at the end of the day, what we have to learn about. And as an A&P mechanic, you may not care much about chemistry in of itself, but you do care about corrosion and you want to know how to prevent it. So let's learn about how chemistry connects with corrosion. So we have galvanic corrosion right here, and I have this video embedded already into a different part of the presentation, so I'm going to skip ahead of this. But let's do an explanation of what galvanic corrosion is. At this point, you've already taken a look at things. Galvanic corrosion is the tendency of metals to return to its natural state through chemical reactions. So in this particular situation with galvanic corrosion, what happens is that you have two different metals that are touching. Like, for example, sheet metal and a rivet of two different materials. Maybe one's aluminum and the other one's steel. And what happens is that when you have the two different types of metals that are made out of two different types of elements, electrons want to go from one to the other. And when electrons flow between these materials and cause that redox reaction, the oxidation reduction reaction that we discussed earlier, then what's going to happen is that whatever material is losing the electrons, which is called the anode, is going to start to corrode. Whereas the cathode, which is what gains the electrons, is not going to corrode, but is going to cause the anode to corrode. So there are four conditions that cause galvanic corrosion to occur. There's the presence of an anode, which is the metal that corrodes by giving away electrons. Then there's the presence of the cathode, which is the metal that receives the electrons and causes the anode to corrode. And then there's also the presence of an electrolyte. An electrolyte is a material that conducts electrons, things like water or salt water. Maybe you think of Gatorade when you think of electrolytes, probably because there's a lot of water and a lot of salt in Gatorade, hence why there's an electrolyte. And then there's got to be electrical contact between the anode and the cathode, or in other words, the surfaces have to be touching in some way. So that being said, you may be wondering, what's the role of an electrolyte here? And I have an analogy here that I think might help you. Let's say that we have electrons in the anode, and then we have the cathode over here. And the electrons want to travel over to the cathode. What happens is that the electrolyte acts as the bridge, and essentially it's that surface that conducts the electrolytes over to the cathode. So again, if that helps you to think about it, that's great. I've got a couple of questions for you. Why don't you go ahead and knock those out? Thanks for getting those done. Let's move on. So, just for your information, there's a galvanic grouping of metals. And essentially what they do is they rank metals based on how anodic or how cathodic they are. And anodic, like we discussed before, anodes is your tendency to give away electrons, whereas if you're a cathode, you have a tendency to take electrons from the anodes. So this galvanic reaction chart is called the electrochemical series of metals. And basically, I have a version of the chart right here. I have a link to it right here, and I even have a QR code for you right here. So my invitation to you is to take a moment, pause the video, scan this information, or pull it up on Google, again, galvanic reaction chart, and find a chart similar to what we have over here. And then, once you've done that, I'd like you to answer the following 2 questions. Go ahead. Thank you for getting those questions done. Let's move on. So, galvanic corrosion, right? A few other things you should know about. If the surface area of an anode, again, that's what's giving away the electrons, is much smaller than the cathode, then it's going to corrode faster. And here's my explanation for that. Basically, if you have a larger amount of surface area that's taking away than what is able to give, then it's just going to cause that to corrode faster. What's stealing is going to be a whole lot larger than what's able to give. And I have some diagrams of what that looks like over here. Again, what you have right here is a cathode as the sheet metal, and then you have a rivet over here that is the anode. And essentially all the sheet metal around it is eating up the anode, which the rivet is made out of. So again, something important for you to notice. Another thing worthy of mention as well is that if mercury spills on an aluminum surface and interacts with an electrolyte, what happens is that corrosion is very severe and difficult to control. The reason why is because this is another form of galvanic corrosion. You have aluminum, which is acting as the anode, while the mercury is acting as the cathode and taking away electrons from the aluminum. To show you a video of what that looks like, I have it set up over here, and I think you'd be very interested to see it.
In terms of its application, aluminum amalgams are commonly used in chemistry for reduction reactions. As we saw earlier, metallic mercury wasn't amazing at attacking the aluminum, so for these reactions, we usually use a soluble mercury salt. The general idea here is that mercury keeps exposing fresh aluminum, which really likes to donate electrons.
Okay, so you can see right here another example of a galvanic reaction, and that's the mercury and the aluminum. Again, mercury and aluminum don't mix well together. It corrodes really quickly in the right set of circumstances, so we got to make sure we keep those apart. Now that we've gone over this, you know enough information to be able to answer a few questions. Why don't you go ahead and get the next 5 questions answered for me. Now that you've got those questions done, and we've talked a lot about galvanic corrosion, let's go into a couple other corrosion concepts that you're going to need to know in life and in the FAA exam. So there's also something that's called grain-related corrosion. And what ends up happening is that you have, first of all, intergranular corrosion. Intergranular corrosion is what happens when corrosion concentrates on the boundaries of metal grains. Here's a diagram of what end grains look like, and you can see a cross-section of it over here, and you can see what it looks like in the context of some sheet metal and a fastener. So basically what ends up happening is that during the heating and cooling of the aircraft, the grains become less uniform with each other, and you can see that shown right here. And what happens when you have heating and cooling of the aircraft and the grains become less uniform is that it's more susceptible to this intergranular corrosion. And probably the biggest cause of it is improper heat treatment. This is very difficult because you can't find this very easily with visual inspection. You usually need non-destructive testing to do that. And additionally, you have certain metals like aluminum alloys and stainless steels that are very susceptible to this. So intergranular corrosion, we've discussed that, but there's actually more severe versions of intergranular corrosion that is called exfoliation. And what happens is that when enough of this intergranular corrosion builds up, it can cause entire metal sections to flake from the rest of the part. So now that you understand that, I have a number of questions for you to answer. Let's go ahead and get those done. Thank you for doing those. Now let's wrap up with some mechanical corrosion. So we have fretting. Fretting is when you have two tight-fitting mating surfaces, like, again, rivets and plates. They move, and even if they move slightly, it can allow even something as simple as salty air to get in the gap and essentially go in and be the electrolyte that causes corrosion and attack unprotected surfaces. So one other name that they often have for fretting corrosion is called smoking rivets. You can see right here that you have the mating surface of rivets and sheet metal, but because of fretting corrosion, you can see corrosion around each of the rivet holes. Again, that's a classic example. When you have your two tight-fitting mating surfaces, that's fretting corrosion. There's also stress corrosion, where essentially you have a corrosive environment combined with sustained tensile stress in the aircraft. So very often what manufacturers and AMTs will do when they're trying to work the metal that they're using on the fuselage of the aircraft, they'll do something that's called shot peening, where they'll shoot BBs and make dimples inside of the metal, and that automatically produces a compressive force within the metal that can counteract the tension that causes stress corrosion. So now that you understand that, why don't you go ahead and get a couple more questions done for me, and that'll be it. We'll see you in the next video.